This, we proceed with analysis of systems which contain equilibria involving salts of limited solubility in water. So far, we looked at the simplest possible case, like saturated silver chloride solution, where solubility for the salt can be calculated straight away from the solubility product constant, KSP, for the salt. Why? Because neither component ion of the salt, in that particular case silver ion and chloride ion, show any Bronsted-Lowry acid-base properties of consequence in water solution. But now, we take a look at S calculation, solubility calculation for salts, where you cannot possibly get the solubility calculated correctly straight from KSP. Why? Because for these cases, the anion component of the salt will be a Bronsted base, which is a considerably stronger Bronsted base than water. And on preparing the saturated solution of the salt, this base will react with water, hydrolyze, and produce its conjugate acid and hydroxide ion. So guess what? To understand this aspect of semi-soluble salt equilibria, which is the most common aspect, we're right back to acid-base chemistry. Which is why we have paid attention heavily to acid-base chemistry before we start this kind of stuff. You'll see the same applies to forming complex ions. You will see the same applies to electrochemistry. Many species and substances have a stability which depends heavily on Bronsted-Lowry acid-base chemistry in water solution. That's why we do the acid-base stuff first, because it lays foundation for all this other stuff that we wish also to do. So, back to semi-soluble salts, where the base chemistry of the component anion of the salt has got to be considered. In such cases, the solubility for the salt can be calculated if you pay attention to, in addition to KSP, KB for the base. And we already know how to do that. Just adds another equilibrium consideration. You think a system like this can also get sufficiently complicated so that we'll have to pay attention to material balance and charge balance? You're damn right. That's why we've done that already as well. Let's get at solubility for calcium carbonate. Its KSP is this. But there is its observed, measured, experimentally determined molar solubility. Silver chloride. The solubility is equal to the square root of KSP. Because when silver chloride dissolves and puts silver ion and chloride ion in solution, the silver ion and chloride ion don't do anything else chemically. So their molarities remain equal, and remain equal to the solubility of silver chloride, which for that case is square root of KSP, given that that's the only equilibrium which applies to that system. But for calcium carbonate in equilibrium with its component ions, we can say if the calcium ion molarity and the carbonate ion molarity were equal, then the solubility would equal the square root of KSP, and the square root of this KSP is about 8 times 10 to the minus 5. It's a little bit less than 8 times 10 to the minus 5. Well, 1.4 times 10 to the minus 4 is almost twice 8 times 10 to the minus 5. So now we're recognizing, at the minimum, you cannot correctly calculate solubility from material like calcium carbonate from the KSP equilibrium alone. Let's try an experiment. Experiment which I expect most of you have already done. How many of you have investigated the properties of calcium carbonate in 46L by the work in assignment 3. All right, then I don't even need to talk about this. You all know about this, don't you? I got some deionized water. I took it from there when we last met, but I didn't use it, so I left it in the cylinder. Indicator phenolphthalein. You're familiar with the acid-base properties of phenolphthalein. Put in a good slug. At a pH of around 9 or above, phenolphthalein becomes a distinct red-pink. But at pHs lower than 9 and above, it remains colorless. Is that clear? Because clear does not mean colorless. Clear means transparent to light. Strawberry Kool-Aid is clear, but it's hardly colorless. In any case, our deionized water usually runs a little bit of acidic because of CO2 absorption. You folks in 46L, you're well advised. The first thing you should do every time you go to laboratory is to take a quick look at the pH of the laboratory deionized water, because that's the stuff you're going to be using to make all your solutions. What have you been finding for the lab deionized water, pH-wise? I want a number. About 6? It's okay. Well, this should probably also show about 6. This is the deionized water which comes from the deionizing system in this building. Still deionized water. Let's put some calcium carbonate in here and see what happens, since we've laced the system with an abundance of phenolphthalein. See any color development at the bottom where the calcium carbonate bulk thereof has gone to? By continuous shaking, I have readily and rapidly produced saturated calcium carbonate solution. In this case, in the presence of phenolphthalein indicator, a distinct red pink. So this is screaming at us. Whatever the pH is of this system, it's above 9. In fact, if we were to look more carefully, or determine more carefully this pH, we'd find out it's about 10.0. If you go after this pH with a tuned up pH meter to 2 sig figs, you'll find out the pH is 9.95, which is 10.0 to 1 sig fig. So that verifies what we have here already stated. Upshot, in saturated calcium carbonate solution, which we just prepared, the calcium ion molarity is considerably greater than the carbonate ion molarity. Because once this equilibrium is established and the calcium ion is put in the solution, the calcium ion sits there, it engages in no further chemistry. But there's another tug, so to speak, on the presence of carbonate ion and its molarity. Here's the tug. The carbonate ion doesn't just sit there. It engages in reaction with water to produce bicarb ion and hydroxide ion, and that's what accounts for the production of hydroxide ion, the color of this system, and the fact that it's a pH of about 10.0. So let's take a quick fast look at Kb carbonate and see how it relates to this issue. Here's Kb carbonate value. There's the chemical version of the equilibrium constant. And in this system, water plus water reaction won't mean anything. So to this, we can apply x squared over m sub I minus x. Now, if we didn't know the solubility, the 1.4 times 10 to minus 4 value, could we approximate the molar solubility using this equilibrium based on the fact that the pH is about 10.0? Of course, that's what we've done here. 2.1 times 10 to minus 4 would be equal to 1.1 times 10 to minus 4 quantity squared, because the hydroxide ion molarity at pH 10.0 is 1 times 10 to minus 4. The bicarb molarity would equal the hydroxide ion molarity. So Here's x squared over m sub I minus x. We'd calculate m sub I. We'd get 1.5 times 10 to the minus 4. That's pretty close. Not bad. So based on this, if we ask the question, to what extent or percent has carbonate ion gone away, has hydrolyzed by this reaction with water, because hydrolysis just means reaction with water, we get 67%. In fact, the hydrolysis or ionization extent of carbonate ion is even somewhat greater than that. Because true S is not 1.5 times 10 to the minus 4, it's 1.4 times 10 to the minus 4. We got that up there. And the true pH, so if you put the value in for the bicarb molarity at 9.95 pH, it's pretty close to this. That the percent hydrolysis on the order of 70%. You can put in the numbers and do the arithmetic if you so wish. The main point being that after introducing carbonate ion to this solution system, the bulk of the carbonate ion goes away. So, after having realized that the bulk of the carbonate ion goes away by this hydrolysis process, what do you think about this KSP reaction? It's a legitimate reaction, but is this reaction Stoke for stoichiometric? Is that a stoichiometric statement? If it is a stoichiometric statement, if that reaction is a stoichiometric statement, then how will the calcium ion and carbonate ion molarities compare? They will be equal. For silver ion and chloride ion in saturated silver chloride solution, that's fine. Provided that for the saturated silver chloride solution, you don't put an additional source of silver ion in the system, or an additional source of chloride ion in the system, or something else in the system which will react with silver ion, or something else in the system which will react with chloride ion. Well, this is not stoichiometric. It's a legitimate reaction equation because it certainly keeps with the chemistry that occurs when you dissolve calcium carbonate in water. No question about that. But you better be careful if you do calculations with this reaction system, because stoichiometric it is not. The calcium ion molarity in the system is about how many times bigger than the carbonate molarity? Of course, more than 2/3 of the carbonate went away, didn't it? It hydrolyzed about 70%. So for this system at equilibrium, how does the calcium ion molarity compare to the carbonate molarity? Well, we know it's a lot bigger. A lot bigger by what factor? Here's the calcium ion molarity. What's carbonate molarity relative to this number? Well, if 70% of it went away, how much of it is left? 30%. So the carbonate molarity is 30% of this number. So the calcium ion molarity is this number, and the carbonate ion molarity is only 30% of this number. Well, what's 100% compared to 30%? About 3 to 1? A little bit bigger than 3 to 1, isn't it? Okay. So we have now at least introduced ourselves to equilibrium considerations involving semi-soluble salts, where KSP alone will not allow you to calculate salt solubility. What do you think about calculating solubilities for sulfides? you will investigate some salts, some sulfide salts, which are quite slightly soluble in water, in 46L disturbed. Copper sulfide, zinc sulfide, silver sulfide, being the three sulfides whose properties you will investigate. For saturated silver sulfide solution, how do you think the silver ion concentration will compare to the sulfide ion concentration in saturated silver sulfide solution? In saturated silver sulfide solution, how do you think the silver ion concentration will compare to the sulfide ion concentration? I want a better comparison than just saying greater. Infinitely greater. I like that. Why do I like that? You going to find any sulfide ion in this pot? Hell no. So I don't care what the silver ion concentration is. If it's 1 mole per 63 bazillion trillion gazillion liters, which isn't much, it's still infinitely greater than something which is nothing. See how the game plays? Now let me ask you another question about the silver sulfide system. Since that stuff is so stable in water, even though sulfide ion is a strong base which reacts with water to an extent of 100%, when you make saturated silver sulfide solution, or if you did, an observed system pH, you'd get 7.00 to 2 sig figs. How about that? What's that telling you about the solubility of this stuff?
It isn't.
Incredibly small. Because all the sulfide that goes in solution hydrolyzes and converts to hydroxide ion, NHS minus. So you know damn well you're not putting much of that stuff in solution if you wind up with a saturated solution pH of 7.00. So if you're going to calculate that solubility, you're going to need KSP for silver sulfide. What else will you need? Will you need KW? You're damn right. Because it's a very, very dilute solution, isn't it? Ah. And what will you need beside KSP silver sulfide? KW for water. What else will you need? KB for what? KB for what? KB for what? HS minus. Because that's the base that will be present in that system. All right. That's a look to the future. Now ask this question. We reminded ourselves, or at least I hope successfully so, but I don't think the notes, our notes, are particularly clear about this. One more reason why I got to get these damn things rewritten. If only there were 3,000 hours in a day, I could get at this. In the last 3 days alone, I've been asked to generate 11 letters of recommendation. In the main, these letters of recommendation come from folks like yourself who've been with me and who've gone on to become successful, and you want support to go to graduate school or medical school and whatever have you. And if you've done a good job with me, I'm more than happy to support you. Or from graduate students who've taught with me, who are looking for jobs. I also was asked 2 days ago by a new organization, I guess you can call it that, on campus, which is interested in trying to see to it that minority students succeed in university. Hey, I'm for this. And so they come to me regarding this class and chemistry laboratory. You think there are many minority students in chemistry laboratory? You know how many enrollees we have in chemistry laboratory this term? That's 45L and 46L enrollment added together. 2,600. How many students do you think I'm running into with this request? About 200. Stuff takes time. This is one of the reasons why I tell my colleagues, that's why I'm here all the time on weekends. Because weekends is when I write quizzes, weekends is when I write exams, weekends is when I do developmental work, like work on my notes. But weekends is only 2 days of the week. Because during the regular week, I haven't got a whole lot of time to do the stuff I really want to do. The other stuff I need to do. You know, I'm not really objecting to doing it. But it's just part of life. That's okay. Because I can very, very emphatically and happily tell you, you're looking at one lucky guy. You know why? Because I'm doing what I like doing. I know people with PhDs who have jobs that they can't stand, but they keep the jobs because they're making a lot of money. That's terrible. Spend your existence doing things you don't want to do because of money? Barf! I don't want any part of that. I mean, Machen, for instance, he can have his $500,000 a year. I wouldn't trade what I do for his job for Lovener money, for nothing. Because I'm doing what I want to do. I have a chance directly to help the future of this country. That's you folks. He has a chance to run around in bologna sauce with politicians and stuff like that. I don't want any part of that life. Wear a suit and a tie every day. Yuck! The tie strangles the blood. Causes me to have headaches. I can't think right. Wear a tie? I don't know who the hell invented those damn things. They ought to be shot, in my opinion. You think I'm strongly opinionated? You're damn right. Back to this. We reminded ourselves. That's what got us started talking about the silver sulfide system and stuff like that. That what a KSP equilibrium really involves is the chemistry that occurs when you take a salt of limited solubility and dissolve it in water. So it may not necessarily be silver chloride in equilibrium with silver ion. It may not necessarily be like silver chloride in equilibrium with silver ion and chloride ion. In that case, fine, dandy. Because there's no other chemistry that occurs. Well, we've already looked at. If I write KSP for calcium carbonate as the calcium ion molarity times the carbonate ion molarity, which is legitimate, I have to be on my toes because that is not a stoichiometric reaction, and that's not a stoichiometric equilibrium constant, because the calcium ion carbonate ion molarities are nowhere near equal. So how about this? Could I use this reaction equation and calculate its value and call that KSP for calcium carbonate? Does this in fact not state directly the chemistry that occurs when calcium carbonate is dissolved in water? Because this reaction shows the carbonate hydrolysis directly. It shows the production of hydroxide ion and bicarb ion. Textbooks don't dwell on this. I don't know why. That is a more legitimate representation of KSP for calcium carbonate than that. But textbooks always use that, and I've never seen them use that. I don't know why. Because textbooks which know what they're doing have recognized that silver sulfide KSP or silver oxide KSP, there's no sulfide ion or oxide ion in those expressions. How can I refer to the concentration of something which is not existing? So as we've already noted, silver sulfide KSP is silver ion molarity squared times HS molarity times hydroxide ion molarity. Because those are the things which are in the system that come about as a consequence of dissolving silver sulfide in water. And hydroxide ion and bicarb ion, we've recognized, are in the saturated calcium carbonate system. That's a more legitimate representation of KSP for calcium carbonate than that. But this has got problems as well. Is that a stoichiometric statement? Yes or no? No, why not? What does that equation, what does that reaction equation up there not show you, but you know is in the system? The remaining carbonate ion. There's about 30% of it still there. That doesn't show you that. That suggests all the carbonate ion goes away. You got to be careful about this stuff. It's one more reason why this chemistry stuff is tough. And I say, politely but emphatically, the hell with all these people who say Horvath is tough. Chemistry's tough. This Horvath happens to be a person who wants to show you what chemistry's like. Chemistry's tough. And when you water it down to the point that it's not only full of ambiguity, it's in many cases dead wrong, which is what you get from these stupid general chemistry textbooks all the time. You think I'm going to let that garbage in this classroom? No way. Never. Out the door it goes. Oh well. Back to chemistry, enough sermon. A different carbonate of limited solubility. Don't know what it is. Call it a hypothetical carbonate. We make a saturated solution and observe a saturated solution pH of 11.0. The question is, how does the solubility of this carbonate? If stoichiometrically it's like calcium carbonate. See, 2 plus ion and 2 minus carbonate ion. So this is a 2 plus metal ion, whatever it might be in carbonate ion. But this shows a saturated solution pH of 11.0. How does the solubility of this carbonate compare to the solubility of calcium carbonate? Is this carbonate the same solubility? Do you think if it was the same solubility, since they have the same stoichiometric composition, since this material has the same stoichiometric composition as calcium carbonate, that if this had the same solubility to show you the same pH as saturated calcium carbonate solution? That seem fair? But it doesn't. It shows a pH that's a good deal higher. 1 pH unit higher. Has a hydroxide ion molarity that's 10 times greater than saturated calcium carbonate solution. So I repeat the question. How does the solubility of this carbonate, MCO3, compare to 1.4 times 10 to minus 4? That's the solubility of calcium carbonate. This carbonate is more or less soluble? More, you betcha. Because more carbonate went in the solution. That's how you got the higher pH. Right? Aren't we recognizing that it's carbonate that accounts for this pH? So the more carbonate goes in the solution, the higher the pH. Right. If you go to the laboratory and take a look at the pH of 10th molar sodium carbonate solution, 10th molar, you're going to get a pH of about 12. All right? Question 19.8. Silver carbonate happens to show the same saturated solution pH to one significant figure as calcium carbonate, 10.0. How does the solubility of silver carbonate and calcium carbonate, how do they compare? About equal, aren't they? They put the same amount of carbonate ion in there. Enough said. Now, silver sulfide, which we talked about a moment ago. This shows a saturated solution pH of 7.0. I think it's 7.00 to 2 sig figs. Pretty sure. Might be 7.01. Woohoo! With that, the solubility of silver sulfide compares how to the solubility of calcium carbonate? Compares how to the solubility of silver carbonate? What are the factors that we have to consider? Sulfide ion is a strong base. Sulfide ion in solution hydrolyzes to an extent of 100%, doesn't it? So if silver sulfide and silver carbonate or calcium carbonate, if silver sulfide had the same solubility as calcium carbonate, the same solubility as silver carbonate, what would be the pH of the saturated silver sulfide solution compared to 10.0? Be greater, wouldn't it? Because all the sulfide that goes in a solution hydrolyzes. So have the same solubility. Silver sulfide would be putting as many moles per liter of sulfide ion in the system as calcium carbonate puts carbonate ion in the system, as silver carbonate puts carbonate ion in the system. So if it had the same solubility, the pH of the saturated silver sulfide solution would be greater than 10.0. Ha ha! But it's 7.00. So this is screaming at us. The solubility of silver sulfide compares how to the solubility of calcium carbonate and silver carbonate? It is a whole blank lot less, you betcha. Now then, let's go to page 19.8. This is in the notes. Now let's take a look at the solubility of calcium carbonate by applying some additional chemistry to the system. In this case, the additional chemistry we're going to apply is to take a water solution and put some buffers in it to fix the pH at 8.00. And in this water solution, we're now going to compute the solubility of calcium carbonate, imagining that the only impact of the buffer is to maintain pH at 8.00. No reaction with calcium ion or anything like that. Okay. Before we do this calculation, how will the solubility of calcium carbonate in this system, the water system buffered at pH 8, how will the solubility of calcium carbonate compare to this number? I'm listening because I'm asking you. Let's think about the chemistry before we do any computations. The solubility of calcium carbonate in water solution buffered at pH 8.00 is absolutely and flatly guaranteed to be greater or smaller than the solubility of calcium carbonate in straight water. The solubility of calcium carbonate in this solution buffered at pH 8.00 is guaranteed to be greater than 1.4 times 10 to minus 4. That's the solubility in straight water. Or less than 1.4 times 10 to minus 4. Because I got a feeling that you'll all say, well, it's not the same. So what's your vote? The calcium carbonate solubility at pH 8 is greater than 1.4 times 10 to minus 4. How many vote for that? No looking around, just me. Told you, any crooks in here, it's me. I'll steal you blind, watch out. Well, in this case, I'm finding that not too many of you are voting correctly. Isn't this solution pH 8.00 100 times more acidic than pH 10.0? 100 times more acidic. If you want to kill bases, do you make the system acidic or basic? If you want to kill bases, do you make a system acidic or basic? Basic or acidic. You want to kill bases. You're going to add, you want to kill a base. You're going to add an acid to it or another base? Acid, bingo. This solution is 100 times more acidic. It's pH 8, right? So you're going to kill the carbonate much more effectively, right? So the calcium carbonate solubility's got to go up. That's the chemistry. That's the part you got to think about first. And if you don't do that, the calculations you're going to be engaging in won't mean a damn thing to you except confusion. Now then, what do you think about the extent or percent hydrolysis of carbonate at pH 8? We found out at pH 10, I erased it, that the hydrolysis extent of carbonate ion was about 70%. Remember that? What do you think about the hydrolysis extent at pH 8? Well, you think it'll approach 100%? Or at least be a good deal greater than 70%? Absolutely. So with that being said, I'm going to use this equilibrium. Our other version of the KSP for calcium carbonate. So I'm going to write K equals this. And then to do the calculation, I need the K value. How do I get the K value? I look at this equilibrium reaction, and I let it talk to me. What does it tell me as it talks to me? It tells me I got calcium carbonate as a reactant. That guarantees that this equilibrium constant contains KSP for calcium carbonate. And on the right I see bicarbon hydroxide ion. And I have already recognized that the bicarbon hydroxide ion come from what? What do hydroxide ion and bicarb ion come from in that reaction system? They come from carbonate ion. And when carbonate reacts with water to make those things, what property of carbonate ion am I looking at? Kb, right? I already know what I'm looking for because I let that damn thing talk to me. Now how do I get this achieved arithmetically? Oh, this is really tough. I do this. Because when I do this, it allows me to use this version of KSP calcium carbonate, which is 6.2 times 10 to the minus 9. And the remaining terms, bicarb times hydroxide divided by carbonate, that's Kb carbonate. All I got to do now is put in the numbers. So I put in the numbers and I crank. I think something on the order of 10 to the minus 13, something like that. 10 to the minus 12. Where are you? 1.3 times 10 to the minus 12. And now if I wanted to, I could write a table of alternate KSPs and say, hey, that too is a KSP for calcium carbonate. Nothing wrong with it. Because it shows the chemistry which occurs when calcium carbonate goes into water. Okay? Now then, tell me, how can we get a handle on the various possible forms? This is a material balance question. How can we get a handle on the various possible forms of carbonate-containing things in this system? Well, before we get at this handle, tell me now, please, the various possible forms of carbonate-containing things in an aqueous system. The various possible forms of carbonate-containing things in an aqueous system from a pH standpoint. Carbonate ion itself, hydrogen carbonate ion when carbonate ion collects 1H plus, and quote-unquote H2CO3. So I'm going to write something on the board and see if it looks reasonable to you. First we write this. Because when the calcium carbonate goes into solution, which involves putting calcium ion in solution, does the calcium ion engage in any other chemistry? No. So the solubility of calcium carbonate is certainly equal to the equilibrium molarity of calcium ion. And now we've recognized that the solubility of calcium carbonate, in addition to being equal to calcium ion molarity, is equal to the sum of these three molar concentration forms of carbonate. Because when carbonate reacts with water, it either becomes this and or this. So if I sum up the equilibrium molarities of this, I got to get the same value as this, which is S calcium carbonate. Now we ask one more question. How can V for various forms I'll put quotes on carbonate because I'm referring to all these things. How can the various forms of carbonate in this system be compared? I'm listening. Ka what? Can't have Ka of all of them because carbonate ion doesn't have a Ka. Can I use carbonate ion Kb?
Yes.
Will that allow me to compare the equilibrium molarities of bicarbon carbonate? Yes, because Kb bicarbonate has got bicarb in it. Now how do I get the H2CO3 in there? How about Ka for HCO3? How about Ka for HCO3? How about Kb for HCO3 minus? Let me get this right. How about Kb for HCO3 minus? How about Ka for H2CO3? Because KH2CO3 allows me to compare the equilibrium molarities of H2CO3, quote unquote, to carbonate, bicarb. And Kb bicarb shows bicarb plus water makes hydroxide ion and quote unquote H2CO3. So I can use Kb bicarb or KaH2CO3. Just like I can use Ka bicarb or Kb carbonate to compare the equilibrium molarities of carbonate to bicarb. So, this is where we're at. You know what to do. It's in the notes. Take a look at it. So you will be following along with what we tackle next time.